نه من نمیخوام دیده باشم.
با حرف بزن اینجا بزن نزدیک این دودی مشکی حرف این صدا
We are going to start in a couple of minutes. Will come in. Good evening, ladies and gentlemen. I'm delighted to have everybody here, especially Dr. Azimlu, who accepted to give us this talk. My name is Mohaddesseh Azimlu. I'm the president of the Sharif University of Technology Association, and this is a worldwide association with chapters all around the world, and one of the active chapters in Toronto. We have monthly events, and this event is jointly held with Iranian scholars worldwide. That I would like to thank them for all the help that they brought. Also, we had supporters, North York Physics Group and Shanaf Group, that I also thank them for being here and for all their support. Before continuing and before inviting our speaker, I would like to ask Mr. Arya, the president of the Iranian Scholar Worldwide, to also give a short welcome note, and then I will do the introduction.
Hello everyone, and welcome here. My name is Reza Arya. I'm the president of Iranian Scholars Worldwide. It is my pleasure to have you all here, and it is my pleasure to have Dr. Azimlu and Dr. Zahir here. We are cooperating with SUTA, Sharif University of Technology Association, and Iranian Scholars Worldwide together in order to bring you the best quality seminars and talks that we are able to. Thank you so much for coming, and I cut it short, so Dr. Zahir will introduce our honored speaker and our honorable speaker and continue with the program. Thank you.
Thank you, Reza. So before we start, just a couple of, first I should also thank the University of Toronto and Dr. Mustaqimi for helping us to get this nice amphitheater, and also thank particularly the ISW equipe for making possible to have this event webcast real time, so that other people from around the world also can watch and listen to this nice talk. And this is our first time doing this, so I hope that it goes well. I will let you know if it does or not. Dr. Azimlu is from Farzanegan High School, and those who know Farzanegan High School in Tehran, and they probably already appreciate that this is one of the top best high schools for girls in the capital of Iran. She pursued her physics degree, the Bachelor of Science degree, at the Sharif University of Technology, where she was also involved in having established a club, Sharif Astronomy Club. Then she continued her studies in Tehran University, one of the other great universities in Iran, where she got her Master of Science in Physics, and she completed the thesis for that degree in Inter-University Center for Astronomy and Astrophysics in Pune, India, if I pronounce it correctly. For her PhD, she came to Canada and had her PhD from University of Waterloo in 2009 in star formation. And she also worked in Western University in London, Ontario, and Harvard's Smithsonian Center for astrophysics. She is currently an ambassador of the Microsoft Worldwide Telescope project. Without further taking your time, I would like to invite Mrs. Azimlu.
Hi everybody, it's a great pleasure to be here tonight. Thank you for coming. Thank you for Mr. Zabir to have this brief introduction. Tonight I'm going to take you to a brief journey of small wonders of the sky, and I wish you join me in this journey. So, as you said, the first slide, I'm going to talk about the star formation and planet formation, how the stars and planets are forming from the gas, and finally, I will talk about our solar system a little bit, and then other planets in other solar systems. But first, start with how to make a star. This is the only star that we can see such a nice picture of. This is our own star, which is Sun. And this is the only star that we can see a nice surface of like that. All the other stars are just tiny points. So what do we need to make a star? All the stars are made of hydrogen gas. So first of all, we need hydrogen. How much hydrogen? Lots of hydrogen. So 100 to 1,000 solar mass hydrogen. And what is the condition of this gas? This is actually the hydrogen which is made at the Big Bang, when the universe was started. When the universe was made after the Big Bang and after inflation and when everything was stable after that, we only had hydrogen and helium. About like 75% of the gas in the universe was just hydrogen, the rest was helium, 25% helium. And that was mostly all the universe was made of. But that was enough to start creating stars. So we have enough hydrogen in the universe, we don't worry. More than 100 or 1,000 solar mass. But we need dense gas. Just very low density gas in the sky, in the universe is not enough. We need some condensation somewhere to start producing stars. And this density is still much, much lower than the best vacuum you can create on the Earth. It's 1 to 10 atoms per cubic centimeter. We cannot get to this vacuum on the Earth. But that's high density in the universe. That means high density in the sky. And that's good enough to start a star. But we also need some glue. We need to keep things together and collapse things together with some kind of force. And that's gravity. It's everywhere. We don't need to worry about that. These are some of the star-forming regions. That's my favorite one. This is the Iranian Nebula, or M42. This is one of those high-density regions in the sky that I mentioned. This high-density region is still much, much lower density than the vacuums that we can create in the labs on the Earth. And this is another one. This is probably one of the most famous pictures that Hubble Space Telescope took. This is not from Hubble Space Telescope, but you probably recognize these pillars of creation at the center. So we have a gas, about 100 to 1,000 solar mass cloud, and we would like to start a star. We turn on the gravity. Of course, this cloud needs to have special density, temperature, radius. If it's a very, very hot cloud, it's a safe rule. We cannot collapse a hot gas because the pressure doesn't let us to do that. So we need high gravity with enough mass to collapse a hot, dense gas. So we turn on the gravity. What happens? Actually, this gravity, if you look at these flashes that shows what is the amount of the gravity, the force of the gravity that we have here, it's not exactly the same in all the places because, of course, our gas, our cloud is not homogeneous. It doesn't have a nice spherical shape, so different parts of gas, different parts of our cloud are experiencing different size of gravity. So what happens is that actually our big cloud fragments into smaller regions. And each region again has a gravity. And each smaller part, again, starts to collapse into the denser core, and that procedure just continues till we get to stars. So that's why most of the stars are forming in groups and clusters. Like the one we already have in Orion Nebula, which is about like 300 to 600 newborn stars. When I say newborn, I mean not a few days old. 100,000 years to a few million years old. These are baby stars. And they are going to live for billions of years, like our sun, which is only 5 billion years old, which means it's only mid-age star. This is another example of the stellar cluster. This is also a very young cluster, about 10 million years old. By young, again, I mean order of million years old. So what happens to these individual stars? How they start from the gas and then accrete into one dense star? Usually when we start with the big cloud and then fragment into smaller region, still the gas has its own inside internal dynamic. So the fragments of the gas may have some rotation, they collide each other, we have friction, so we have some dynamic of the gas. And when you just turn on the gravity, it wants to collapse everything into the denser region of the core. But you cannot get rid of the angular momentum. You need to somehow get rid of the dynamic of the gas and the energy of the gas to collapse everything into a smaller region. So everything is starting to rotate around the protostar or the denser core at the center, and then rotates faster and faster. Like when you have a figure skater, when she wants to rotate faster, she closes the arms. The same happens to the star. When you have lots of mass at a distance, very, very distant from the center of your system, it has lots of energy, lots of dynamic, but when you collapse everything into a smaller region, everything starts to rotate much, much faster, and all the potential energy of this big, big gas, when it collapses into the core, it's like bombarding. So you are releasing a huge amount of energy of this gas, a huge amount of potential gravity of the gas into this small core. So when you're bombarding this core, what happens? It gets hotter and hotter and hotter. How much? Actually, to start a new star, to start nuclear reactions inside the star diffuse hydrogen into helium, you need to get to a few million degrees, a few million centigrade. And it happens easily in a star. And when the core is getting enough mass and enough temperature to start a nuclear reaction, we call it a star. Now a star is born. And still lots of mass and gas is still same. Pleiades is probably one of the most famous clusters that we see in the sky. You don't need any telescopes or anything to see this very beautiful cluster in the winter night sky. This is actually an almost old cluster. Most of the gas, you may see that, most of the gas is back to the interstellar medium. Only a few hundred stars, that only 7 of them could be seen with naked eye, are remaining in the cluster. And this is what happens to most of the stars. They form a cluster, but if the cluster is not massive enough or doesn't have enough members, then the stars are going back to the interstellar medium, and but all these are inside the spiral arms of our galaxy. So this is where our star sun also starts from. Actually, this process is not very efficient. You may start from 100 solar mass gas, or 1,000 solar mass cloud, or even much, much larger cloud. But at the end, you may have only a few stars. What happens if we don't have enough hydrogen to keep this process going on? Some stars are massive enough to start the reaction to go to the rest of the chain. Now burn helium, make carbon, make calcium, make other heavier elements, up to iron. Actually, iron is the most stable element you can create through the fusion inside the star. These are all reactions that produce energy. Iron is the most stable element. If you want to go beyond that, you need higher energy. Actually, you need to spend energy to create elements heavier than iron. So, where those other heavier elements are coming from then? How we have our gold rings, how we have plutonium, how we have all these other elements coming on the Earth. That's it. First, starting with our own sun. Our sun is running out of hydrogen. What happens after that? Actually, when there is no fuel at the center, when you turn off the oven at the core, there is no energy to keep all this big ball of gas stable. So what happens is all this gas is collapsing into the core right at the beginning, like when the star is forming. So all this huge energy is released and makes the core much, much hotter than what it needed to actually start a new reaction and do the nuclear reaction again. So that reaction may start again. You don't have enough hydrogen, but you may get to burn some helium or other elements. So that reaction happens and occurs in a very, very short time. So what happens is that all the gas which is surrounding becomes hot in a very, very short time. By short, this is really short. This is just days or weeks, or which comparing to the astronomical time, this is really, really short. The star, the rest of the star pops, and again going back to the universe. We call this object a planetary nebula. There is no relation between this object and planets. The reason that this object is called planetary nebula is because when the first time they were observed through a telescope, they looked like planets. They looked like Jupiter or Saturn. They had a surface and they were colorful. So by mistaken or whatever, they were just called planetary nebula, and that's the name that we still name these objects. But a planetary nebula is actually the end of our star. That's the end of our star. Most of the gas that has been collected in millions of years and have been stayed there for almost 10 million years, a tiny fraction of gas at the core has been used and give us the energy that we are using now. We are having created during 10 billion years of its life. But then, at the end, most of this gas is going back to the universe again. So, actually, the universe has a very good recycling system. The gas is collecting, collapsing, making the stars, going back to the universe, and again, it's going to be used. So, part of the heavier elements that have been formed in the stars go back to the universe in this process. You may notice this tiny white point at the center. Just remember that. We'll go back to this. This is another example of planetary nebula. So they may have different shapes. They may have several collapses, not just one. When the star collapses, again, it starts some reactions. It burns heavier elements. Again, it pops. And when it pops, it gets cool. When it's cool, again, gravity can take over and collapse again. So this process may occur and happen several times and make these different patterns that we see here. Mini micro explosion first, and then a smaller one repeated after that, and still we have this tiny point at the center. What is this? That's actually the core of the star. The core of the star is very, very dense. It doesn't destroy, it doesn't go away, it doesn't go anywhere. After most of the hydrogen gas is going back to the sky and to the universe, that dense, hot core stays there. It used to be millions of degrees, so it's really hot, but in this process it gets colder. By cold, it still is like 10,000 K or 10,000 degrees, still has the temperature. It's very small, the size is almost the size of a bird, and that's why we call it a dwarf, but it's small and it's hot, so it's white. So the color that is emitting is white. It's like when you, that's how we know what's the temperature of the star. When you have a very cold star, it's like you have a fork, you put it on fire. At the beginning, if you just have it close to your face, you may just feel some radiation from this hot fork. But you cannot see it. This is microwave. If you just make it hotter and hotter, it starts to become red, and then green, and then blue. And when it gets really, really hot, it becomes white. This is how we know what's the temperature of the star. We look at the star. What's the color? Red. This is the coldest star, 3,000, 4,000. Look at our star. Oh, it's yellow. Our sun is about 6,000 K. When we look at the star and see it's blue or white, we know that, oh, that's a really hot star. So we know that these remaining of the dead stars, like our own sun, the white dwarfs, are really hot because we see their color. And we can measure their temperature by the color. But these are really, really dense. If you just take 1 teaspoon of the mass of the white dwarf, it may weigh like an elephant. So that process happens to low mass stars. By low mass, I mean almost solar mass, up to 8 solar mass. This is mostly what will remain of a low mass star, 5, 6, 8 solar mass. What if we have a heavier star, a larger star, a star that can get to produce iron, 100 solar mass star? Actually, what happens at the end to these stars are more dramatic than this very nice path to the star, to our sun. They are destroyed actually in a big, big explosion. So from this tiny point that we cannot see, or sometimes barely can see, the star may be 100,000 times brighter than what it is in an explosion. Actually, you can see these explosions in other galaxies. That's why they are called nova or supernova. You don't see anything in the sky, and then just by sudden, something pops, and it's a very bright star, sometimes for a few days, sometimes for a few weeks. You can see them by naked eye if it happens, but unfortunately, we're not lucky enough. Mostly 1,000 supernova happens every year in our galaxy, but they are not close enough to be seen by us. If we are very lucky, probably we can see one in our life. So that's the dramatic explosion that creates most of the other heavy elements. So your beam has been created in a supernova explosion, or the other heavy elements that we have in this room. So again, all these elements, thanks to stars, have been created in an explosion when a massive star is dying, and have set and created all these elements that we need now. That's what will remain as a dead star. This is after a supernova explosion. That's the Crab Nebula. It's also mostly made of hydrogen, but now we know it also carries lots of other heavy elements back to the interstellar medium, which is going to be recycled for new stars like our own sun. But again, the core of that massive star also is very dense. It doesn't destroy during this explosion, it remains there. But it's very, very, very dense, even much, much denser than the white dwarfs that we saw. Only 1 teaspoon of that was the weight of an elephant. The density of the neutron stars, we call them neutron stars because they really have the density of the core of one atom. Most of the atoms are mostly empty, right? You have a very tiny core, proton and neutron, and the rest of the atom is electron, it's mostly empty space. But the core itself is very, very dense, where the neutron and protons are. And what we have here as a neutron star is like a huge atom core. It's just a center. And because the star was rotating, most of those angular momentum, most of the rotation of that star remains in the core. So these cores are rotating very, very fast. 100 times a second, 1,000 times a second, about that. So these are rotating really, really fast. And because they still have lots of charged particles, like electrons and protons and neutrons don't have charge. electron and protons there, they have very strong magnetic fields. So consider that you have very strong rotating magnetic fields. What they create? Just radiation. These are very, very good sources of radio emissions and very, very accurate radio emissions because their rotation is very, very accurate. These are actually the most accurate clocks that we have in the sky. The first pulsar, they're called pulsar because when they are rotating like this, when they point to the Earth, they give us a pulse, they go away, they come back, they give us a pulse, they go away, they come back, they give us a pulse. So they're actually sending pulse. And these pulses are very accurate, they are repeating, and very accurate at the same pattern, the same period. So actually when the first pulsar was discovered, astronomers thought that, oh, aliens. We are receiving radiation in radio wavelengths, very accurate pulses from somewhere in the sky that we cannot see anything. And so they were wondering, hey, what is it? They were really thought that probably this is coming from an intelligent source. And then later it was realized that, oh no, this is just a data star. And sometimes we have a really massive star that even that little neutron star cannot resist. And the core is much more collapsed and dense that it becomes a black hole. It's dense enough that even light cannot escape from it. If I just drop something up, it will come back to the Earth. If I drop it with a higher energy, it goes higher and again it comes back to the Earth. If I want to escape the gravity of the Earth, I need an escape velocity which is about 11 kilometers per second. And if we get to that velocity, we can escape from the Earth. But for a black hole, even the speed of light is not enough to escape. Even if radiation going up from the black hole is going back to the black hole. That's why they're called black hole. No light is coming directly from them. But we can see them somehow. We can know where they are because when all the other materials around them are getting swallowed by the black hole, they are radiating lots of X-ray energy. They are rapidly collapsing to and being swallowed by the black hole. And during this process, when they're rapidly falling into the black hole, they are radiating X-ray. So an X-ray source and a strong X-ray source could be a candidate of a black hole. Or sometimes they are in binary systems. We have a black hole and we have another star which is still living. It's not dead yet, and survived the explosion of the massive star which made the black hole. And then you see one star is rotating around something that we cannot see. One star is rotating around an unseen point. That would be another candidate of a black hole. Okay. So we started from beginning of the star, how it lives, how it dies. Let's take a break and go to planets. I'm glad to take you to a journey of an extrasolar planet. Scary? Yeah, thanks God, our Earth is not that close to its star, so it's not that hot and burnt. This planet actually was discovered only a few years ago, and it's very close to its star, to its own sun. It's 10 times closer to the star than Mercury is to the sun, so that's why it's so hot and burnt. So, let's move to make planets now. Actually, stars and planets are forming at the same time. It's not that we have the star and then we have the planet. Let's go to our first gas. Now we know it's not just gas. After some cycles of having stars, they die, they recycle to the interstellar medium. Now this gas actually has more elements. It also has some dust. By dust, we mean anything which is heavier than helium. So carbon is dust, oxygen is dust, silicate is dust, iron is dust. So anything which is not hydrogen and helium, we call it dust. So now we have gas, which is after like 5 billion years. This is when our star was formed. More than that. Our universe is about 14 billion years old, and our sun was formed only 5 billion years ago. So it was formed mostly when the universe was 8, 9 billion years old. So it had enough time to create some massive stars, kill them, make enough heavier elements for us to create our own Earth and our own solar system. So we have this gas, which also has lots of dust. Dense cores, which are proto-stars, are forming. We know that the gas is rotating around this protostellar core to form the star at the center. The mass actually accretes toward the center through this disk. It rotates and falls into the central star. It loses energy when it's doing that. And you notice that, some gaps are appearing within this disk. This proto-planetary disk is not uniform. These are actually where planets start to form. Mostly when the star is forming itself, the planets start to gather the dust and gas around them within the disk too. Then they clear up their paths if they get massive enough, and finally we can end up in a stellar system. So, after you may have heard that Pluto is not a planet anymore, and probably some of you wonder, hey, we love this planet. Shame to astronomers, why you are not accepting this to be a planet anymore? It has two reasons. Actually, one, more planets, well, I should say more objects. More objects and heavier bodies were discovered beyond Pluto, which were rotating around the sun, and they were also massive enough. So what we're going to do, change the definition of solar system every year and say, now we have 9 planets, now we have 10 planets, now we have 12 planets. And then these exosolar planets were discovered. The planets which are rotating around other stars. How we should define them also planets. How they are compared to the planets that we have in our own solar system. So astronomers should have to come up with one unique definition of what is a planet and what is not a planet. So the first rule to accept an object to be a planet was it should have a central star and it should rotate around that star. Pluto does that? Yes, check. The second rule, it should have enough mass to make this round spherical shape. Because you know, when you do not have enough mass for like a rock, it just stays like a rock. So it doesn't become spherical enough or round enough. You need enough mass to make that, to just collapse it into a very nice round shape. Well, I know, Earth itself is not really mathematically spherical, round spherical object, but physicists accept that to be round enough. So it should have enough mass to make a round spherical shape. Pluto does that. Yes, Pluto is also nicely round and spherical. But then the third rule was added, which works also for exosolar planets or exoplanets. That object which is going to be accepted as a planet should be massive enough to clear up its path when it's forming. it should be massive enough to attract all the other objects around itself and make a nice clear path around itself. So, does Pluto do that? No. Pluto has a very nice moon, Chiron, which is mostly half size of it, and there are many, many other objects, mostly around Pluto, which are smaller, and but Pluto has not been massive enough to collect all those masses and all those debris of the solar system around it. So actually, Pluto failed to clear up its path around the sun. So, but that is a good definition now, because now we can use it to define if an object found around another sun or another star is a planet or not. These are some real pictures of the disk. That was a nice artistic picture of the disk. This is what the best telescope in the sky, which is Hubble Space Telescope, can see from the disk. Actually, the disk is what we cannot see. This is the disk. We are looking at that proto-planetary disk age on. This is another disk. This is a disk. And because it has lots of mass and it has lots of dust, it's actually obscured the light coming from the gas behind it. So that's why we can discover, oh, this is disk. So these are actually where new planets are forming now. Mostly the proto-stars form, and now we are looking at the new planets here. 5 million years ago, our solar system looked like this. Let's take a profile and inside of this donut-shaped disk. This is where the star is. But we have many different sized particles inside this disk. We have dust, we have still lots of gas left. How planets are forming within this disk? We have tiny parts of the debris of other stars, or the dead stars, from a few millimeters to a few centimeters. They have also lots of ice. This ice is not like just water ice, everything just frozen gas will be ice. These are like dirty snowballs. When they hit each other, they melt, they catch together, they become larger and larger. And that's how you can go from millimeter-sized dust particles into centimeter-sized dust particles. And when this particle, this dust gets big enough, it can collect all the mass around it and become larger and larger and clear up its path and become a planet. But there's a big problem here. How we get from centimeter-sized dust into a few meter size? Actually, when these objects, when these particles inside the disk, which are going actually moving into very different directions towards the center, and they are all rotating around the star, when they get to centimeters, a few 10 centimeters and above, they have enough energy that when they collect each other, actually they destroy each other. So this is still an unsolved problem in astronomy. That yes, we know how to from millimeter size get to centimeter size, and we know when we have a big object, a few 10 meters, how to like the size of this building or just this room. That particle will continue its life and collect all the other mass around it to become a planet. And we still don't know how to get from this centimeter size to this size. Dr. Mohaddesseh Azimlu is an Iranian astronomer who works at the University of Milky Way, and he particularly works on this issue. And they actually do some experiments in lab to find out what composition and what conditions may let us to pass this meter barrier from centimeter to over meter. What we're talking about, exosolar planets, are actually very, very new in astronomy. It was always believed that we have other planets, other stars have planets, some of these planets even have life on them, and there were projects to look for intelligent life on other planets. But none of them have been directly discovered since 1992. So yes, only 22 years ago. Actually, the first announced planet was in 1988 by the Canadian group from British Columbia and the University of Victoria. But that planet was not confirmed since 2003. And the first planet actually was announced to be found around the pulsar. You remember that pulsars are very accurate clock. So if everything happens that blocks that radiation coming toward us, we will get that very quickly. Okay, we can see that next. So this gap here and this small absorption here in the pulse coming from the pulsar was showing that, oh, there's an object here. Probably this object is not originally the planet of the star, because probably all the planets around that dead star has been destroyed during the supernova explosion. But still, the pulsar or neutron star is a very massive object, so it can capture or collect other wandering objects around it and start having a new planet. And that planet was actually discovered by a receiver telescope, which is a radio telescope, and it may surprise you that actually this telescope has been formed and built inside a dead volcano in Puerto Rico. So you cannot actually move this telescope. You have to wait for the object you want to observe to pass above this telescope. And this is the largest single-dish telescope, radio telescope we have on here. It's 305 meters wide. How else we can discover a planet? We wish to observe them directly. This is what we would like to see when we are looking for a planet. But unfortunately, this is only an artistic picture. We can never see something like that. Only Earth, only the solar system planets, and only our own sun could be seen like this. The surface with the dark parts on it, and sunspots or star spots. That's two are actually the best images you could get from real planets around the star. And what you see here is not actually the star itself. We had to block the star because it was so bright. We had to block the light of the star to be able to get the image of the planet. So what you see here is actually only the residual of the light of the star that could not be blocked. And these are two best pictures of directly imaging of the planets. To get this kind of planet, they should be very huge, much larger than Jupiter, and also very distant from the star that could be resolved in such images. But there's another much easier way. Can you see a planet in this picture? Top over here. This is actually our own sun, and this planet is our neighbor Venus. And this picture was taken 2 years ago, almost, when Venus was passing this way over the sun. Even with naked eye, we couldn't see this. We needed to have a telescope, even to see Venus transiting the sun. So how we expect to see a transit in other planets and other stars? We just need a very good photometer. This is what happens. When you're looking at the star and when you're staring at one star, if you see that the light coming from that star changes in such a profile, then that might be a planet rotating around the star, and we have been lucky enough that looking at this system age on, so the planet is passing through the surface of the star, not above or bottom. And this is actually real data. So you see how close is that? It's not just simulation. So this is the real data of the transiting planets. That's actually the most common way to find exoplanets. You just select some candidates, you look at them, and if you see this pattern of changing light, this is an exoplanet. The next way is, this is also very commonly used method, is changing the radial velocity of a star. What it means? When you have an ambulance passing by and has the siren on, you probably have noticed that when it's coming toward you, the noise is different when it's going away from you. The sound changes, right? The frequency of the sound when it's coming toward you is smaller, the frequency is higher, and then when it's going past you, it's going away from you, the frequency of that sound is different. We call this the Doppler effect. And the same happens to the light. When you have the source of the light coming toward you, the wavelength changes, and when the source of the light is going away from you, it goes towards a larger wavelength. The same happens when a planet is rotating around a star, and if that planet is large enough, like Jupiter, what happens, instead of just the planet rotating around the star also rotates around the center of mass of the system. This is very, very close to the star itself. So the star is just wobbling or jiggling a little bit around where it is. But that's good enough for us to measure the changes. So this is the planet rotating around the star is rotating around the center of mass, which is this green cross here. And the yellow, the blue and red lines here are the specific lines that we see in the spectrum of the star, and this is how they change. To red, to blue, to red, to blue, when the star is also rotating around the center of mass. So it's very nice when we have a cartoon like this. But it's not really easy when we look at the real spectrum. This is a real spectrum of a star. And what we see here is actually 100 parts of that spectrum cut and sits within one frame. So in fact, we will start from a larger wavelength, almost red color, and then go all the way to the infrared, to the ultraviolet and to the violet. So what you see here is actually a long, should be a long frame, starting from here, ending up to here, but it didn't fit in one image, so we had to cut it. And you see many dark lines here. These dark lines are absorption from the elements that we talked about. Every element has its own pattern of the absorption. Because it has different levels of the electrons, the electron pass through different levels, so every element has its own unique signature of pattern of these lines, which you see them like this. Like humans, we have fingerprints, and every fingerprint is just unique. So elements also have these unique fingerprints. But it becomes very difficult when you have hundreds of elements and molecules, and all of them have their own fingerprints, and it means many of these lines. And they are all gathered together and they're captured together within one spectrum. It's like that the detective wants to find a suspicious person in a party from fingerprints on a glass which has been touched with 100 persons. It is possible, but it's not really easy. We can do that. And actually, the change that we see in the spectrum, the wobbling of the star that makes a little bit red shifted, a little bit blue shifted, a little bit red shifted, blue shifted, is very, very tiny. So this is what you see here. That's how much these lines are just getting moved on a big spectrum. So, not an easy job, but possible. And astronomers are doing that, and by this, we can find what is not finding an exoplanet, but also find what is the velocity of this planet. And then that helps us to find the ratio of the mass of the planet to the star. The third method is using gravitational lensing. That was actually first predicted by Einstein, that when the light passes by a massive object, the light will be bent. The gravity can bend even light, because it bends actually the space around it. So the light path passing a heavy object, a massive object, will be bent. So a star should be used like a lens. It was actually observed and it was tested in an eclipse by the sun, and it was observed that, oh yes, even our sun is massive enough to bend backward stars. So it happens to all other stars, and when a star with a planet is passing by in front of the background star, the very background star of the galaxy, the light coming from that background star is bent, so probably you may see a ring, or it might be magnified, or you may see more than one image of that star, and it changes when the star passes by the background star. So we know what is the pattern when one star passes here. But when we add a planet to that, that pattern changes. Instead of having just these nice two images of the background star, a third one may appear here, and the pattern of this magnification is different. And just by measuring that and seeing a different peak, we realize that, oh, there was another object here That's probably the planet. This is actually a very good method to measure the mass of the planet. So these are the three most commonly used methods, but there are many others to find exosolar planets. Based on this knowledge, a spacecraft was launched into space in 2009. Kepler, the spacecraft, or Kepler satellite, was named after Johannes Kepler, who spent almost his own life studying the planets. And the mission of the Kepler was looking for exosolar planets. Of course, Kepler couldn't look for all the planets in the sky, so it got a tiny region of the sky in one of the spiral arms of our own galaxy. And if you want to know how small is this region, just make your fist where you're along the arm. And the area which is covered by your fist is the area which is covered by Kepler vision in the sky. So that's only part of the sky which is studied. But Kepler took 145,000 stars to look at them and look for transits. So Kepler is just looking at the transits. It has photometers looking at individual stars and is looking for that pattern of transiting planets. And yeah, that's a picture of the spacecraft itself. And this is what it has found so far. 2,930 candidates. 962 of them are confirmed to be exosolar planets. And this is as of last month. This picture is a bit older. And in total, we have other methods of looking for planets too. So actually, in total, we have almost 4,000 candidates so far, and 1,800 of them has been confirmed to be really exosolar planets. And these numbers is going to change. So if I give this back the next 6 months, probably these numbers are different. Actually, I had to adjust them from the time I gave 6 months. And this is a group photo of all the discoveries of Kepler since last January, well, last year, 2013. This is our sun. So you see that most of the planets are actually discovered around very, very tiny star like our sun. But some of these planets, like this one, or these two, or this one, or these two, are actually orbiting around the stars much larger than our own sun. The first very exciting discovery of Kepler was finding a planet which is orbiting around 2 stars. Well, you may ask, hey, what is this 16b named from? All the candidates, all the exosolar planet candidates found by Kepler are named by numbers. So Kepler 16 means the 16 candidates found by Kepler. And A, B, C, D are the number of the first planet in that star, the second planet in that star, the third candidate in that star. So Kepler 16b was actually one of the first discoveries of the Kepler. And it's not a big one, it's mostly smaller than Jupiter, mostly the size of Saturn. And it orbits around its own star in 228 days. So it's much larger than the Earth, but it's much closer to its own star. And these are mostly the planets that Kepler can find, because if you want to find the transit of a planet, the planet should be very close to the star, and it should rotate very, very fast. So you can take one period of the planet and then wait for a second one to confirm that, yes, it was a planet. It was not just one object passing by it once. So it seems that what George Lucas had in Star Wars, 2 stars setting in a planet, was not just an imaginary planet. This planet has been discovered now. And let's look at an artistic animation of how this planet is rotating around 2 stars. We have one main star, and then one smaller dwarf star, rotating around the main star, and then the planet, which is rotating around both of them. Unfortunately, this system is not stable. It may stay for a few million years, but unfortunately, the planet will escape or will collide with the stars, and this system is not going to stay forever. If you think this is easy to find, to make a solar system or a stellar system, I would like to introduce you another game. This is also online, Super Planet Crash. It gives you the opportunity to become God, choose your star and your planets, and make them rotate around the sun, around the star. Go and try and see how much stable solar system we can make. That's the solar. The other main question that Kepler was looking for was, okay, are we alone? Is there anybody out there? Are there any planets having life on it? So Kepler was looking for stars which are in, for planets which are in habitable zone of their star. Habitable zone is defined as the distance from a star which can have liquid water. The temperature and pressure on that planet is suitable enough to keep liquid water. Well, we know that all the kind of lives are not dependent on the water. We have viruses which doesn't need water. But for now, this is the definition that we have for habitable zone. And as you see, the smaller stars have habitable zones closer to them. Larger stars have habitable zones farther because they're hot. So the region that the planet can survive and have liquid water should be farther from the star. This is our sun. Mercury, Venus, and Earth is the best place within a habitable zone, mostly at the center. Mars is at the edge. So it probably, when it was closer to the sun, or when the sun, probably when it was closer, it would have some type of life, not now. And then the rest of the planets definitely are out. The first planet which was discovered by Kepler, Kepler 22, was also one of the first discoveries, was within Kepler 22, which was within the habitable zone of a star, which is smaller than the sun, but has a very nice habitable zone. It also rotates around its own star at around like 200 days, but it couldn't be confirmed an Earth-like planet. It's mostly a gaseous planet. Most of the rocky planets like the Earth are those which are much closer to their star, because when they are closer to the star, they cannot actually keep the gas around them. Jupiter, Saturn, Neptune are farther from the sun, so they can keep the gas around them, but Mercury, Venus, Earth, Mars are close enough that are heated up by the heat from the sun, and they actually lose the gas. So actually the hydrogen gas, which is around these tiny planets, has been evaporated, and only the rocky core has been remained. All the other planets have their rocky core and still have lots of hydrogen around, and they're a gaseous planet. But very recently, just probably a month ago, another planet was confirmed that yes, it is in a habitable zone, it is a rocky planet, and it has, it is like the Earth, mostly the same sensibility. Kepler 186. So far, Kepler has discovered around 3,000 planets. Most of them are actually Earth's, not Earth size, they're like Neptune size, and it's a bit larger than Jupiter. But that was the mission of the Kepler. All the other planets discovered before were just huge gaseous planets like Jupiter or larger than Jupiter. Kepler didn't find them, but Kepler was a very, very successful mission to find Earth-like planets. So it gets us to the dream question of human being. Are we alone? Is there anybody out there? What's the possibility to find anybody, other intelligent creatures in the world? Frank Drake actually introduced this equation about 1960s, 70s, when it was the rush to the space and everybody was looking for aliens. So that equation says, how many stars do we have in our solar system, in our around Earth? Probably just a galaxy. 100 million, almost. Now we know that. How many of them are planets? We didn't know that around like a few years ago. Now we know 100 billions of stars have planets. How many of them are habitable planets or Earth-like planets? 40 billion of these planets are like Earth, and they are within their habitable zones. So very, very, very possible to have one of them have life. But do they really have life? That's the question that we still don't know. Do they have really complex life? Or any intelligent technology to contact with us? And by the way, if they had this, probably in the past, have been destroyed? Have they just on time to contact with us? We have the communication skills only for past 100 years. 100 years in the scale of the astronomical time is nothing. So are they existing at the same time, having the same technology to contact us? We don't know. And we still have a long, long journey to go. Thank you.
Excellent. Before we start the question and answer, I just had an email from one of our friends in Italy that said that he could actually watch the webinar. I just wanted to tell everybody it works. Thank you very much for you and all the technical team for making it happen. So we have lots of time for question and answer. Please, Brad. Yes, please.
Is there a possibility that our sun could go from yellow to white? Is that no such thing as a stupid question, right?
Okay, I probably need to repeat that. Is there any possibility that our sun goes from light to white? The answer is no. Actually, when the star is formed and has its original mass, then it stays the same way most of its life. So our sun is now 5 million years old. It's going to be stay yellow for next 5 million years. But if sun had another companion, if it was a binary system or a multiple system of two other different stars, and if they had collided or there was a mass going from one star to the other, which we see happens in some binary stars or some system of stars, that may happen because if the star can get enough mass, it becomes larger, it becomes hotter, and it changes the color. Unfortunately, it doesn't happen to our sun because it doesn't have a
companion. My question is about pulsars, or you said that the core of the star is made of neutrons. Is there any theory or like how that core came into existence, like how the atoms were stripped from electrons and protons?
The question is that how a neutron star is formed. What's just a neutron? That's the name of neutron star. It's not just neutron. If they were just neutron, they wouldn't have magnetic fields, right? You need charged particles actually to have magnetic fields. The pulsars, most of these are coming actually from mathematical equation in high energy physics. That if an explosion like that happens, what would be the remain? And from what we are seeing from pulsars, the rotation speed and the radiation we get from that, these are just a model that what the pulsar should be like, or what should be. These are actually not directly observable measures. These are all on the paper of mathematical observation, actually mathematical measurements. But they make also some predictions. When you make a model, you also predict that, okay, if an neutron star is like this, then we should see this. And actually that prediction comes true. For example, one of these predictions or one of these coming from the models is that most of the surface of a neutron star is made of iron, and charged particles can easily move through this shell, and that's why we have this very, very strong magnetic field. And that's true. That comes, we can actually measure the magnetic field of pulsars.
That was the question.
Also, you explained that one of the ways that you could see if there was a planet around another galaxy, outside of our sun, was if you could see how the way the light shifted, right? So if we were to check if the planet itself had other bodies going around in a way in which the light is also seen from the planet coming?
That's a very good question. The question is that, if I understood this correctly, is that the pattern of change when the planet passes in front of the star, the light drops, and it goes back. So that's actually what we see. That's what you asked, right? The transit. So if another object passes, we make the same pattern. How we know that it was a planet or another object? So we don't know. That's why when we find a candidate, we look at the spectrum, we go and look with the other methods to confirm that this is a planet. That's why we have many candidates. They stay candidates till we confirm that they are real planets. For example, we see that change in the light pattern again and again. Or we find the spectrum of it, we get the spectrum of the star, and we see this change in the spectrum periodically by passing the planet.
Yeah, of the life cycle our star, you mentioned that the end point is a white dwarf. I think you said it was 10,000 degrees. Does that slowly decay as the star? The final heat death and life cycle of the star?
The question is that the white dwarf is hot now. What happens to it? Does it stay the same way or it decays? Actually it does, because it's emitting lots of energy now. It actually can become dimmer and dimmer and colder. And probably at the end it becomes just a black dwarf because it doesn't have energy to produce more light. Unless it collides with another object or something like that happens.
What is the period?
Oh,
Is that
100 million years or so.
okay,
So we actually haven't seen any dimmed brown and dimmed white dwarf in the universe yet. Our universe is really young. We still have stars that haven't died. We have early stars that was formed when the universe was beginning, like the stars are about 13 billion years old, and they haven't died yet.
just to follow up to that question, what about the situation of brown dwarfs? Are they as a brown dwarf, being that it doesn't have the mass required to become a white dwarf, or is it a white dwarf or something midway to a white dwarf that's just dimmed out?
The question is about brown dwarfs. If they are white dwarfs, dimmed to brown dwarfs, what is a brown dwarf first? The brown dwarf was actually unborn stars. When you have the protostar, but if this protostar cannot get enough mass to become a star, to start nuclear reactions at the core, it becomes a brown dwarf. It's still a very massive object, but it's not massive enough to get hot at the core to start a nuclear reaction. Some of them even start doing just helium, just hydrogen to deuterium, but deuterium is not getting to helium. And if you cannot do that, you are not producing any energy. And many of these brown dwarfs actually have lots of deuterium at the center, but that was not enough to make them stars. To be precise, actually, astronomers are defining the objects that were hot enough to make deuterium are brown dwarfs. Those like Jupiter, which are massive enough, but not are massive, but not massive enough to start. Even like hydrogen to deuterium chain are sub brown dwarfs. So, but don't forget the names. We have many brown dwarfs in the sky. Actually, Dr. Aurora, who are in Czech University of Technology in Iran, is working on that. And they were looking to count how many of these brown dwarfs are in the sky. Are there like only a few of them, or many of them? And actually, there are plenty of them in the sky. And they were discovered with the same way by microlensing, by the gravitational lensing, when they pass from in front of the back of the star. So yeah, we have many of them, and they will stay the same, like the debris of the star formation process, and they will stay the same just as wandering objects unless they were taken by the star as a planet, like Jupiter, or they just collide each other and become massive enough to make a star.
So would that mean that Jupiter is sort of like?
Yes. Sub-brown dwarfs. It's 1,000 times smaller than, but it's a huge gaseous object.
So just a general question. My question is not very technical. So recently, Professor Hawkins made a comment about black holes. You mentioned black holes there, but from what I understood, he was saying that black holes do not exist or they cannot exist. Can you shed some light on that?
The question is about black holes that Professor Hawking made a comment on didn't exist. Actually, the argument was about if any information can get out of a black hole or not. And the argument was that no, the black hole is black, nothing can get out of it. But now we know it's not really true. If you add quantum mechanics to black holes and the decay of the particle just at the edge of where the black hole starts, which we call this the event horizon. The event horizon is where the photon cannot escape. We don't know where is actually the real age of, like, the material age of a black hole. The horizontal, the event horizon is where we cannot get any information of the black hole. This is where the sun goes, where the light cannot escape from. So, but if a particle decays right at the edge, and like a photon decays into electron and a positron, the electron goes toward the black hole, but the positron escapes. Then what? We can get some information about the black hole. And if you add also quantum mechanics, then you can tunnel through some potentials. And again, these are all discussions on papers. These are all mathematical equations that if you add rotation then to the particle, then you're adding a potential, extra potential and extra energy to the particle, which is being going to be swallowed by the black hole. Then probably that tiny extra energy can let it escape from. So that was mostly the discussion, and it was finally came up that black holes are not absolutely black. They leak. They leak some information.
Sorry, are you greedy with questions?
That's
The life cycle of stars using higher atomic mass elements is a beautiful idea. Is there any way to sort of look forensically at the matter that's around us to determine how many generations it's gone through? Is there any way to look sort of project backwards and infer what is this matter around us? How many generations of stars is it from?
That's a very, very good question. The question is that by measuring the elements around us, do we know how many stars have been goes around to create these elements that we have on the Earth, for example? Yes, we can. Actually, when you recycle more and more material, then the abundance of the higher elements is getting higher and higher. So that's actually the way that we discover which stars or which part of the stars are really old and they are just from the early universe, from the initial gas of the universe, because they lack any heavier elements in them. They are just, when you look at their spectrum, it's very pure. It just have hydrogen, helium, and that's it. And very, very probably technical ones. But as long as it gets more abundant, it gets more heavier elements, you see the abundance of those elements to be higher and higher. If that helps us to say how many generations, that measurement is not that accurate yet. We can say that, for example, when the first stars formed within the galaxy. For example, we know that the center of the galaxy has more recycled mass. Actually, the abundance of the heavier elements at the center of the galaxy is much higher, but when you go to the edge, it declines. So most of the stars which are at the edge of the galaxy are initially older stars. They don't have too much heavier elements, but the ones that have been at the center have been more cycles and have produced more heavier elements. But still, these are not very, very precise just to look at one star and by measuring the abundance of the elements and say how many cycles have passed.
Very much.
My question is along those lines, but it's quite an elementary question compared to that intelligent one. I didn't really understand with the helium and the hydrogen when they're there and they're creating next kind of elements. They're fusing together. Like, is it the hydrogen and the hydrogen and the helium? They come together, and then that makes something else, and then fuses with something else, and it makes something else. And
the question is about the fusion in the stars and how hydrogen is going through making heavier elements. I can show you the table here. That's the table that shows how this reaction actually happens. First of all, you have two hydrogen that diffuse to each other. And yes, that's a nuclear reaction. This is exactly what happens in hydrogen bombs. And it releases lots of energy. And then it creates a deuterium. And then two deuteriums goes to each other. Deuterium is a hydrogen which has one proton and one neutron. The hydrogen atom itself has only one proton at the core and one electron rotating around it. But deuterium is two hydrogen colliding each other, diffusing to a heavier hydrogen which has one neutron, one proton. And then two deuterium go to collide each other, diffuse to each other. Now we have two neutrons, two protons, that's helium. And then the same way. Hydrogen, two heliums collide each other, diffuse each other, make carbon. And that's actually a really interesting game. If you just go play this game, you can make your own star and do all the diffusion and see actually how difficult is it.
Can you go back to event horizon? They said before event horizon. How does it do that? The frequency of the radiation, or the particle shapes out, comes out of the return?
The question is about the event horizon and how from there. If I want to make it simple, it's like we know that the photons also decay into particles. In the same way that two elemental particles may collide each other and make photons, what happens in some nuclear reactions. For example, when you have an electron and a positron, positron is a particle very, very similar to electron, only it has a positive charge. Everything else is just similar to electron. It's like a positive electron. A photon can decay into a positive and electron. The same way that an electron and positron can collide each other and make a photon. So when you are at the edge of the horizon event, and one photon there decays, the electron goes toward the black hole, but the positron escape to the other side, because they go two different ways. Then actually, by capturing this positron that it has lost its electron, you get some information. At least you know that one electron is missed. And this is some type of information that I'm talking about. This is not like a written text or something like that. This is, just very, very tiny part of information that we can get. By information, I mean like a particle that has missing companion. That's an information.
The patch in the sky that Kepler is looking at, is it looking at the galactic center?
The question is that how the region, the patch that Kepler is looking at, was selected. It's actually about, you know that our galaxy is a spiral galaxy. It has different spiral arms. We're looking at one of the very nearest spiral arms to us. We cannot look through our own because it has lots of dust and gas in it. So it's most of the stars coming like through this gas and dust, their light is obscured. So we cannot observe that. The light is absorbed. So we're looking at actually at the next spiral arm. And again, we are not looking through the spiral arm itself. We are looking a little bit above it, just to get rid of the dust in the arm and the dust in the disk of the galaxy. And this is actually a region which has been selected because it doesn't have any bright front star. If you have any bright star just something in the sky, it actually, the light of that bright star also destroys everything and obscures everything. So this is actually a very empty region, and by empty, I mean empty of nearby stars, which if you look at it by naked eye, you cannot see anything there. Most of the stars there are much, much dimmer than we cannot see anything with naked eye if you look at the region of the sky that Kepler is looking at. And it's inside the spiral arm, so it has enough star, but it's not crowded enough that we cannot resolve image of a star. So that's how that region was selected.
Hi, good evening. My question is about Earth. you mentioned about star stuff, right? And that dust comes from the supernova. So if we are star stuff, where is the supernova reminiscence which we came from? Like something like neutron star or pulsar or white dwarf, something has to be there near us. But that's absent. So
the question is that if we are recycled from the star that has left behind a black hole or pulsar, where is that object? We don't know. Actually, the particles which are going back, exploded and pushed back to the universe in that explosion, are traveling very, very fast. So we cannot go back and see what had happened or where we are coming from. That object doesn't need to be very near. Because explosion, the gas is going very, very far from the object that has created. And then that goes to, that gas and dust is going back to the interstellar medium. That interstellar medium itself is rotating around the galaxy. It's part of the spiral arm. And we have lots of tidal forces within there. We have lots of friction. And so it's actually almost impossible to trace back that's where the dust that made dust is coming from. But that's a really good question.
So you say just a pure chance that this dust cloud formed and we came from it, sun formed. So?
The reason is that because we know that the early universe after Big Bang didn't have any dust or any heavier elements. We know that it was only made of hydrogen and helium. So that heavier elements should be formed somewhere. And that somewhere, by now, by our knowledge, by our current knowledge, is just stars. And that's actually a good point about the science. Whatever we say, this is to the best knowledge so far. So probably something may happen like next few years, and a new theory comes up, and new observations and new discoveries, and show that, oh no, you were wrong. This is the new substitution that may work as well.
Thank you.
More questions? I have also a question. On the formula, the direct formula, the one that you have the equation, the first few elements in the formula, you multiply them. I really didn't understand why, how those numbers multiply. First one, I think it was the number of stars in the galaxy, that I understand. Then the second was the number of planets in.
Yes, how many of these stars have planets? We are going to find out how many planets we have.
Why you multiply them?
Oh, okay. Yes. That's right.
It should be a fraction.
A fraction.
Great,
That's actually two.
Yeah, okay.
That won't be the same number. Yeah, the same number of stars, we have the same number.
Okay.
Thank you for
Thank you. No problem. Okay, thank you very much. Everybody, thanks those who watch us everywhere on the world. Have a good night, have a good day, wherever you are. Have a good time of the day.
Yes, it is. It is on YouTube. Or we can search the name of this. Okay.